Hello everyone, this is Shiva. Right. So in the previous example, so we've seen force between point charge and another continuous body. So we've discussed we've discussed for a wire, right, of length L and some point charge, and also a ring of radius, or a uniform ring of radius R, having a charge q and another point charge, right? So please do comment on those if anything was wrong, or if you think I should go through another one, right? So yeah, and this one is a slight variation. They've asked what is the angular frequency, but instead it's just 2 point charges. So let's just go through the question here. So a particle of mass 1 milligram and charge q is lying at midpoint of two stationary particles kept at distance 2 meters when each is carrying same charge q, right? If free charge particle is displaced from its equilibrium position through x, where x is very much less than 1 meter, the particle executes SHM, its angular frequency will be. So we've seen angular frequency for a ring and a small point charge, right? So here we have 2 point charges, right? Stationary particles, they're separated by 2 meters, and each charges q, right? So this is 1 meter, 1 meter. This is the midpoint, right? Here another mass of 1 milligram, right? Mass 1 milligram and charge q is kept. So here this is slightly displaced from its equilibrium position through x. So let's say this is displaced in this manner, right? This is x, this is x, and this x is very much less than 1. So compared to this distance, this x, this displacement is very less. So it is a small displacement here, x. Okay. If before this is displaced, if small charge is kept here, this q will repel this charge in this direction, and this q will also repel this q in this direction. So forces, they balance each other, right? Since Coulombic force is central force, both force acts along the line joining the forces, and q is kept along the line, right, in the in the midpoint. So forces balance each other and q will not move at all. But since we disturbed it, right, we gave it a small displacement. Now this q is here, right, new position of q, and this new position is nearer to this q, right? So this distance is 1 minus x, right, to this charge. To this charge, this charge is at a distance of 1 plus x, right? So 1 minus x and 1 plus x, since distances are different, so obviously field is different. Here the field is more and here field is less, so obviously forces are also different. So here, since this is nearer, this will exert a force in this direction. Now this will acquire velocity and will go somewhere over here, and this will repel this one more, and again this will come here. So in this manner, about mean position, it would oscillate and there would be SHM here, right? So for that SHM, we have to find angular frequency. So let's see here. We know the distances, so let's compute the resultant force, F resultant. So due to this charge, K, Q1, Q2, that is Q square, both are same, by distance square, this is 1 minus x whole square, right? This is in this direction due to this charge, right? Due to this one, it will be opposite, right? Since this is less distance, this force will be more, so I'm taking this minus this. Otherwise, if this is less, you could do it reverse, right? So this would be kq square by 1 plus x whole square, right? So this distance is more, so force due to this charge on this charge is less, so that's why I'm taking minus here. So this is F resultant. So F resultant is equals to kq square if I take common. So this one will be a minus b into a plus b square. So if I take this one 1 plus x whole square, a square plus b square plus 2ab minus this one a square plus b square minus 2ab, right? So F resultant is equals to kq square, so 1 plus x square plus 2x minus 1 minus x square plus 2x divided by 1 minus x square whole square. So 1 x square, so F resultant is equals to kq square, this is 4x, this is 1 minus x square whole square, right? Okay, so we have they said that this small displacement which we have given to q, that is very much less than 1. So if I neglect this one here, in the denominator x I'm neglecting, so 1 square is just 1, right? So approximately I'm almost equating it to 4k q square x, right? Okay, so if I consider this as a resulting force, which is nothing but, since this is doing SHM, I can kind of equate or take it as minus kx, right? If I compare this, the SHM constant here k is going to be 4k q square, right? Where this k is 1 by 4 pi epsilon naught, right? This is SHM constant. So if we do this one here, k is nothing but m omega square, so that is equals to 4k q square. And I asked angular frequency, so omega square is equals to 4k q square by m. So omega is equals to root of 4, k is 9 into 10 to the power of 9. Q was well, we don't know, but yeah, we do know. They're given q square is 10, right? Divided by mass of the oscillating particle, that is 1 milligram. So 1 milligram is 10 to the power of minus 3 grams. Again, if I convert it into kilogram, minus 3, right? Okay, so omega is equals to root of 36 into 10 to the power of 10, this goes to numerator 6, so it will be minus 6 goes to numerator 10 to the power of 16, so this is equals to 6 into 10 to the power of 8 omega radians per second. So this would be your answer. Okay, so I hope you got the concept that whenever there is an SHM, right, usually we get this kind of equation that is similar to minus kx. So removing that k, that is usually restoring force is directly proportional to opposite the side of displacement. So this is one variation, right? By the way, before not before one, like first one and second one, those kind of examples which I have discussed, right? These are all PYQs. This is also PYQ. These are all PYQs. Yeah, not any new ideas or anything. So, anyways, yeah. I'll see you in the next module.